All right. Hey, what's up?
I love your equation sheet you made.
I'm glad. Thank you for actually looking at it. That's
It's pretty well done. I like it a lot.
good because that's what you guys are going to get to use on the exam. So. I'll be ready.
Zach, you got an otter pop?
Yeah, man, they're the best.
Nice.
Pop.
Hey, Jesse, I sent you a private form message so we can get each other's numbers for our group.
All right. It's 12:30. Let's get rolling. All right. Where's that? I got to get my slides up. That would probably be good, right? I guess that'd be good. Hard to tell, really.
Free slides.
Apologize. I apologize. guys. All right. I guess these people can come to class, I suppose. All righty then. We got that going. I am going to do the thing here where I share the screen because, that seems like a good idea to do it. We'll share this screen. Share. No, not that one. There we go. You guys all see the PowerPoint?
Yep, looks good.
Thank you. I've worked really hard.
YouTube.
I worked really hard. Thank you. All right. So let's get started. It says screen sharing is paused. I don't like that. Hold on. We're gonna do that again. Okay. Somebody's trying to join in here.
More than meets the eye.
Okay, here we go. Now we're cooking. Now we're cooking with gas. Let's get started. Dear Lord, thank you for bringing us together this afternoon. Thank you for all the blessings that you've given us. I pray that you would just continually bless us, that you would help us to run the race all the way through, that you'd help us to keep our composure and do the things that we need to do to be successful this year. Thank you for bringing the first week of classes to an end and help us get through the rest. In your name we pray. Amen. All right, guys. So the good news is that we are like a third of the way through this online mess. And we basically survived, right? So yay us. Yay us. Basically. Taylor. I would never lie on purpose. Never lie on purpose. All right. So what are we doing today? Right. We're gonna do things. Before the things though, you might notice that this is actually it says live at the top as it's also being recorded. I put this on YouTube. We're streaming it live right now. When? Right now. You just missed it. All right. We're streaming it live on YouTube. That way I don't have to wait for Zoom to render the video and then send it to me and post it later. This way it will just be posted at the end of class and that will be that. So much more efficient, right? Much more efficient. And that's what we're going to do. Hopefully, let me know if you guys prefer the format from the first class or this one, and we'll figure it out from there. Okay, perfect. So we're going to do some things today, right? We're going to recap last class. We're going to talk about modeling mechanical systems, and we'll probably get as far, if my last class was any indication, we will get as far as translational mechanical systems, and we'll do rotational systems starting on Tuesday of next week. Okay. So that's what's going to happen likely. And even if it doesn't, well, it'll happen. We'll get at least that far. We're not going to go further than that because I don't want two sections that are disparate. All right. Anyway, this was our word cloud from last class, right? We've got ODEs and systems. I'm going to reserve the right to talk about ODEs until later today. We're going to go over them a little bit more. We didn't really do much with it, but suffice it to say that any physical system can be talked about as a linear ordinary differential equation. And we'll talk about that a little bit today. A system is a grouping of elements that are used for some specific purpose. Right. We're going to talk more about systems. A dynamic system in particular is one in which the output of said system relates back to the input and any initial conditions. Right. which means it plays well with ODEs. Eugene Kong 312, that confuses me too. I'm not really sure what to do with that, but thank you for it. Can you guys see the word cloud? Let's start there.
No, it's
No.
blank.
No? All right, perfect.
No.
That's great. All right, let's see. We'll try this one more time. How about now? Can you guys see it now? Still no?
No.
Oh.
We can see it, but we can't see like the words. Like we can see the screen, but whatever we were contributing, we can't see.
Okay, great, perfect, as intended. I'll work on that for next class. I don't have time to troubleshoot that in real time. I'm sure you guys. All right, Pendulum Lab is due next week, not on the 13th, which is this Sunday, but is due on the 16th, right? And then we have a homework due a week from Sunday. The homework was posted in LoudCloud, so you guys all have access to that. Please start it before Sunday night next week. Really recommend that you start it before then. You might want to try starting a few of the problems, this weekend. That would be my recommendation. For the lab, if you don't have a lab partner, please group up with somebody. If you can't find somebody by tomorrow, let me know, and I will try to find somebody to help you out. Okay? But talk to each other, use Discord, do the things, right? Ask people if they want to be lab partners. Speaking of the lab, perfect segue. This lab is the Pendulum Lab, and some of you may have seen the video on YouTube. Dr. D and Professor Price do labs episode 1, which involves the Pendulum Lab. I want you guys to look on LoudCloud, read through the lab, and follow the instructions. By that, I mean you're going to watch the video and create a mathematical model of your pendulum from the data that we have in the video, right? So it's a really exciting video if you haven't watched it. Basically, we made a couple of penduli and we swung them, and we show you video of the cord passing across a protractor, so you know what angle it's at. And you get to choose the sampling, right? You get to do all that stuff. And tell me, basically throw all the positions into Excel over time, and then graph them and make a model, right? But you also have to do a mathematical model, right? You also have to do a mathematical model, okay, using the principles that we use in class. And we'll talk more about that today, later, right? One write-up per group is fine. Remember, I reserve the right to change your groups if after the first lab, people do poorly, right? So if you get less than a 50%, then, well, even if you get close to 50, like just above it, I'll probably switch you to. But if you do very poorly, you're gonna be asked to change lab partners, right? That's how we're gonna do this, okay? I just don't want people to get too far behind, right? Here's a thing, here's a video that might help, right? Can you guys see this video? Is there a video?
Yeah, we could see it.
Okay. If I hit play, let me know if you can hear it. Wait, 1 second. I know how. Okay. We're going to watch a little bit of this. This might be helpful for the lab.
Hello and welcome to the Postcard Professor, where we take complex ideas and explain them in the space of a postcard.
In this video, we're going to be looking through the basics of numerical differentiation. Now, what numerical differentiation does for us is it gives us an approximate derivative in a situation where it might be difficult or impossible to calculate an analytical derivative. What if we only have data points for our function instead of an actual function to use? Well, in that situation, there's no way to calculate an analytical derivative. And so we have to go another path. The basis of this, as for so many things in numerical methods, is the Taylor series. Now, what Taylor's series says is that the function at some point, and I've just named that point x, is going to be equal to the function at another point, and name that x bar, and that's going to be related to the derivative of a function, again evaluated at that second point x bar, multiplied by delta x, and that delta x is just the difference in space between the 2 points. So this is delta x is equal to x minus x bar. And then we have some additional constraints based on higher order derivatives. And we can go on further, but I'm just going to end this with an order of delta x to the fourth. So if you wanted to go higher, just remember that the number in the denominator here is equal to the order of delta x factorial. So this is 2 factorial, this is 3 factorial, the next one would be 4 factorial, which is 24, and so on and so forth. Now, we'd like to use this in order to calculate a derivative, and we want that at a specific point in our data. So let's say that we're interested in the derivative at this point right here. I'm going to call this point I. So at point I, we're going to have an x of I, and that x sub I is going to yield an f sub I, which is just equal to the function evaluation of x sub I. And we can do this for other points as well. So let's say that we go 1 point to the right and start talking about I plus 1. This point right here is going to be I plus 1. And we're just going to name those values x sub I plus 1, which yields f sub I plus 1, which again is just the evaluation of this unknown function at x sub I plus 1. So with this nomenclature, let's go ahead and rewrite our Taylor series. We're going to evaluate our function at x sub I plus 1. So we say that f sub I plus 1 is going to be equal to f sub I. So all of our x bars are now going to be x sub i's. So this becomes f prime, but we say fi prime, and this just means f prime of x sub I, multiplied by delta x. And I'll go ahead and write out the rest for you. This delta x that we have here is going to be x sub I plus 1 minus x sub I. So we're taking this value x sub I plus 1, subtracting off this, and we get this little delta x. Now remember that what we're looking for here is the derivative. So we want to solve this equation for fi prime. So what I want to do is go ahead and isolate this term on the left-hand side of the equation. So I will end up with a negative fi prime multiplied by this delta x, which is going to be equal to f of I minus fi plus 1, and then we have all this other stuff. So finally, we go ahead and solve for fi prime, and we end up with these first two terms divided by delta x. So this is fi plus 1, which the sign has been switched because we're dividing through by negative delta x, minus f of I divided by delta x. And our next term here is this minus fi double prime multiplied by only 1 delta x divided by 2. And then we can keep out writing the rest, but really that's all that matters. So the important thing to note here is that we don't know what fi double prime is. So all of this, we're just going to throw away and call it error. And so we end up with an error that has an order of delta x. So we have additional error terms on here as well, based on the other derivatives, but they're all of higher order, meaning that they're at least delta x squared. So if we're able to decrease delta x, for instance, then those should disappear faster than this error. This first little bit here is what we call a forward difference. And essentially what we're doing with that is we're just connecting a line between these 2 points and calculating the derivative based on the slope of that line. Now, this is not the only way to tackle this problem. The next most obvious way is, instead of using I plus 1, we could also use the point to the left, which we would call I minus 1.
Okay. Sorry. We're not going to go through how to do backwards difference. It's essentially the same, except that you're using the point before instead of the point after. This might be helpful. Right? It might be helpful. Why? You're going to get a bunch of positions with respect to time from you taking your empirical data, right? Your experimental data is all, so it's all positions, right? And times. But your mathematical model, as we're going to see, is probably going to be a function of acceleration and velocity. So how do we get from position to acceleration? Well, you have to take the derivative with respect to time twice. How do we do that if we don't have anything but data points? Well, it's the whole point of doing a numerical method, numerical differentiation, right? So it might be helpful to use that. Maybe. All right. Cool. Everybody okay? Also, Taylor series, as my sign says, Taylor series is the best series. Changed my mind. All right. Don't really, because you're not going to.
Boy, again.
All right. Cool. Just so you are aware, if you're going to do a forward difference equation, you are going to end up truncating part of your data, right? Because at some point, when you get to the final data point with the forward difference, there's nothing left, right? So you can't, literally, you cannot do it on the very last point, right? Because there's no point beyond that. So your data becomes shorter and shorter every time you take a numerical derivative. Before we get into this fundamentals of modeling mechanical systems, I told you guys I would talk a little bit about what is expected for the exam, right? And so let's talk about that. For the exam, which the first one will happen in week 5, what you guys are going to do is everybody's going to take it not in class. Does that mean it's a take home? No, this is what we're going to do. You guys are going to zoom in, right, to take the exam. You're going to zoom into this class link, right? You're going to have your computer with its camera on your face, and then you're going to have another camera, whether it's your phone or another laptop or whatever it is, pointing at your workspace to ensure that your workspace is clear of anything except for the master sheet, which was posted in LoudCloud. Right? The master sheet is the equation sheet that you guys will be allowed to use for the exam. Please take a look at it, familiarize yourself with it, use it for your homework. It is the equation sheet that I would use if I were taking the exam. So it's got a lot of stuff on it. It's got some stuff on it that you don't necessarily need right now, but you will grow into. What I want to know from you guys is if you use it for the homeworks, when you use it for the homeworks, if you notice that there's something that's not on there that you would like to be on there, let me know and I'll bring it up. And if enough people bring it up, I'll change it, right? So I can add things to it and I don't have a problem doing that. But I want to know what you guys think of it. All right. So you take the exam from your dorm, your apartment, wherever it is you are right now, or I guess wherever you'll be in week 5. One camera on you, right? Doesn't need to be on your test. Don't put it on your test. Just show your workspace. Could be as easy as you propping your phone up next to you so that I can see that your workspace is clear of anything but a calculator, your pen, your paper, right? You'll get 2.5 hours for each exam, plus 30 minutes to scan and turn it in. If you turn it in after that deadline, right, on LoudCloud, well, you won't be able to, right? So once the exam window closes, that is it. Okay, so just be aware. You guys have any questions about what's expected with exams? I'm sure we'll go over it again. But if you have any questions right now, let me know. It's really weird to be in a classroom with nobody here. Like it's like dead quiet. Don't particularly like it. Anyway, cool. So it seems like everybody is pretty clear on what's expected there. Jeremy, what's up?
No notes on the exam.
No notes, just the master sheet.
Copy that.
Okie dokie. Well, let's talk about how to model mechanical systems, right? Mechanical systems are, in my opinion, the most intuitive of all of the systems that we are going to cover. Why is that? Well, because if I know that if I push on something, I know what to expect to happen, right? Most of you are mechanical engineers in this class, and I would imagine that you feel the same way, right? Electricity is sorcery, and fluids and fluids and heat transfer is the devil's work, right? That's how everybody knows that, right? Everybody knows that. So, right, we're going to start off with the stuff that is a little bit more intuitive. Now, what physical laws govern mechanical systems, right? Well, we're going to derive our models by applying Newton's second law, right? Sum of the forces is equal to mass times acceleration, or as we're going to come to call it, mx double dot. We're going to stop using acceleration and we're going to start using the second derivative with respect to time of position, which is exactly the same thing, but there's a reason for it, and we'll touch on that later in the class when we get to Laplace transforms. You need to apply Newton's second law to each mass, right? To each mass in a system. Okay, so if you have a system with multiple masses, you need to apply Newton's second law to each and every one of them, right? A mechanical system possesses each of the following, well, can possess each of the following fundamental characteristics, right? There's some inertia. You have a force or a torque that's required to accelerate your body, right? You have a rigid body and there's some force or torque that you need to even get it to start moving, right? There's stiffness, right? And this isn't solely about springs, right? Stiffness is a mechanical property, right, of materials, right? You have Young's modulus that describes the stiffness of steel, right? Stiffness is any deformation that is met with a resisting force or torque. And energy dissipation is the third characteristic. And this is any motion in a resistive medium that causes energy loss. Typically what we will define to be our damping, right? And we'll talk more about these in depth in a second, right? But we're gonna right now jump into inertial elements, stiffness elements, and friction elements, okay? So here's our inertia elements. Before I forget, I put up the first part of the dynamics review on the YouTube channel yesterday. So if you guys wanted to knock some rust off, you can do it by watching that. All right, so what is an inertial element? What is an inertial element? An inertial element includes masses for translational systems and moments of inertia for rotational systems. Yeah, what's up, Jeremy?
On accident, I raised my hand. Sorry.
Okay. So we've got masses and we've got moments of inertia, right? Translational systems use masses, rotational uses moments of inertia, right? We define a moment of inertia as J is equal to the integral of R squared dm in the general case, right? Where our radius changes as a function of mass. Okay, That's great. And for those of you who took ESG-360, right, you remember that Professor Tomford or I made you guys do this by hand, right? And then you got to find, then you found out after we did it by hand a couple times that there's just a table and you're just gonna look it up in the table, right? That's the takeaway. Are you going to have to derive moments of inertia for this class? No. If you need one, you will either be given a table or you will be told which one to use, right? Likely, you will just be given the table and be told, look it up, right? Inertial elements can store potential energy due to position in a gravitational field and kinetic energy due to their motion, right? We hopefully all remember that potential energy is mass times gravity times height, right? It's not really height, it's the change in height based off of some datum that we are using, some reference point. And kinetic energy for a translational system is 1/2 mx dot squared, and for a rotational system, 1/2 j theta dot squared. And we remember that energy is a scalar, right? So we can add translational and rotational energies together if we want, right? Because they have the same units and they're scalars. They're not vector quantities. So that's cool. We're not going to spend a whole lot of time deeply discussing energy methods in this class, right? But some of the things that we do will harken back to this, right? So let's keep it in your head, right? You'll notice that we use J and I bar interchangeably, right, for mass moment of inertia. Whenever we do something in this class, we're assuming that we're doing it about the center of gravity for the most part. We'll see what I mean in a minute. All right, everybody okay with inertia elements? Right. So it's mass or moment of inertia. Okay.
I have a question.
Yeah, so
I didn't write it down yesterday, and I don't remember the notation. Please remind me what the dot over the x means, because I've seen that over other things, but not like an x.
yeah, so whenever you see a dot, single dot means the derivative with respect to time.
Okay, that's okay. Then never mind. Okay, it's the same thing. Never mind. All good.
Yeah.
Thank you.
No worries. All right, anything else? All right. That's inertia, right? It's inertia. I know you're all sad that you won't have to do like your moment of inertia tables and all that, but I think we'll be all right. We'll be okay. All right. Let's talk about stiffness. Let's talk about stiffness. So we introduced it. We said, you know, mechanical systems may have elements that can store energy due to deformation, right? Think of a diving, right? A diving board, you store up energy by jumping on the end, right? And then it gets released and, you know, you fly in the air and you land on your stomach and everybody laughs at you, right? At least in my experience. You can model anything that stores deformation energy as a stiffness element. The most common element that we use is a spring, right? A linear spring has a linear spring constant for translational systems and a torsional spring constant for rotational systems. It's not at all confusing that they both use K without any change, right? So just as a heads up, I will sometimes write K underscore rot for rotation, right? So remind myself whether or not I have a rotational or a translational spring constant. But really, most of the time, when we're not using mixed systems, it doesn't really matter. Just make sure you're doing your bookkeeping, right? You don't want to get confused. Right. Great. So right here, what we have pictured in this figure, right, is a linear ideal spring. Okay, and we'll talk about what makes something ideal in a few minutes. But for right now, just know that this is a linear ideal spring. I want you to notice a couple of things about it, right? The way that we talk about, that we model stiffness, right, specifically for a linear ideal spring, is Hooke's law, right? F is equal to kx, where it's a little bit deceiving, right, because x is Not really x is really delta x, right? Because it's the change in distance from the free length, right? But you get the point. It's a function of position, right? The force is a function of how much I have displaced this spring. Okay. This one pictured here is what we call a fixed spring, because one end is completely attached to something that is not moving, and hence it is fixed, right? You can see that one end here, right? This guy right here, that's in the wall, right? Or as we will hopefully call it, that's in ground, right? So that is attached to ground, right? So it's not moving on the left end. When I pull this, it's really only moving as a function of this position. Now that is in contrast to what happens when we have a spring with free ends, right? So imagine, if you will, for a second, I'm going to go grab this spring that I have somewhere that I've lost. I lost my spring. Oh, there it is. It was over here the whole time. Notice I have this spring here, right? It's a very nice spring. It goes an extension a little bit. You can also compress it. Right, this comes off of an RC car shock, this spring, okay? Now, I want you to see something, right? I'm trying to keep it above my head so you have the white wall backdrop. There's no reason why I have to pull with equal amounts of force on both sides of this, right? Or at the same speed, or with the same displacement. Well, the force, technically I would pull with the same force, but there's no reason why each side has to move the same amount, right? Is there? No. So if x1 is different than x2, how do I figure out how much spring force I have? Well, I need to use relative displacement. Okay, so if you have a spring with free ends, meaning that it is attached between two ends that are moving, you need to use an equation that accounts for the relative displacement of said spring. All right, so the way that this spring is drawn, is this in tension or compression?
Tension.
It's in tension, right? You're pulling it apart, right? So if you were to draw this, right, knowing that it's in tension, the spring is actually applying a force to whatever it's attached to that's pulling it back towards the center, right? Because the spring is being pulled apart, and it's going to fight that, right? It's going to fight that, right? So if you have something in tension, then this is your guy, right? This is the equation you want. If you have something in compression, how does that change this equation?
The signs flipped on the X's.
Yes, you flip the signs. Flip those signs. And what happens when you flip the sign? Well, if you flip the sign, just get that, right? That's what you get. Okay. So far, so good. Everybody all right? This, I'm hoping, so I know it seems strange, but you'll see, once we get into a couple of examples, I think that you'll understand where I'm coming from with the free end versus fixed end. We just need to get there, which will probably happen next week. There's also a couple of homework problems in which this is a thing, so be aware. Okay. Any questions on stiffness elements so far? Right, because all we did was talk about translational stiffness elements, right? So I'm going to introduce to you now rotational stiffness elements. And most of your guys' brains are going to end up on the floor because they're very complicated. Very complicated. If you were like, Dr. D, that doesn't look very complicated. It looks exactly like the last equation, except that it uses torques and angles instead of forces and displacements. You're absolutely right. It's exactly the same thing. You're going to use torque is equal to K times theta, where K is your torsional spring constant. right? And that has units of Newton meter per radian, right? Angle, your angular displacement from the untwisted position is theta, and that is in radians. Here's an important note. Make sure, especially when we get to frequency domain, that your calculator is in radians. You want everything in radians.
Is the pendulum lab also in radians, would you say, or
What's that now?
would you put the pendulum lab in radians, or would you use degrees for that one? It's position, so would it matter, or?
For linear, you're gonna use meters or inches. I don't know. I'm sorry. I must not have heard you right, Trevor.
For the pendulum lab?
Oh, the pendulum. I would probably use radians.
Okay.
It would probably help.
Okay. Thanks.
Yeah, again, we went over it a little bit at the beginning of, I forget, actually, I don't think we may have. I forget if we did units in this class.
We did not.
I don't care what units you guys use as long as you're consistent, right? So, but specific things, radians will just make it easier. Just make it easier.
Easy
English-
as pie.
English units typically don't make things easy to work with. All right. Okay, so right, think of it this way. I've got this ideal torsional spring, and I want you to consider this, right? If I had a rod that I jammed into the wall and I torqued it on one end, right? This too has stiffness, right? It would come back as long as I didn't over torque it past its deformation limit, right? I would be able to use that energy to come back, right? So it's important to note that when we're talking about stiffness elements, we're not just talking about springs, right? If we're talking about a spring element, it's anything that has stiffness. It doesn't have to be an actual spring. It can be something that, a way of us modeling stiffness in a mechanical system. Okay? So they don't necessarily have to represent an actual physical spring. Okay? Here's a picture of various springs. I know, please. It's beautiful. All right, so full disclosure, I am not going to have you use these equations or pretty much ever for anything. But I want to make sure that we've seen them. Right, so you could figure out the spring constant of a translational spring for a coiled round wire spring by using this equation where capital G is the shear modulus of elasticity, N is the number of coils, D is the wire diameter, and R is the coil radius, right? And we could do that. What is another way that I could have you guys figure out the stiffness of a spring?
Like Hooke's law, or?
Sure, you could do it in SolidWorks, right? But what's like a physical experimental method that I can use?
You just test it out with like a specific number of weight and then like how far it moved and then calculate it that way.
Exactly. Right, so this is the part in class where I give you guys a bag of unknown spring constant springs, right? And I tell you to all figure it out, right? And I give you like a mass and a ruler. No, because that's boring. Nobody wants to do that. That serves no purpose. If we had a rod or a shaft in tension or compression, we could figure out the stiffness of said rod by using the equation below here. That's K is equal to E times A over L, where E is Young's modulus of elasticity, A is the cross-sectional area, and L is the length, right? And so I think this makes a lot of sense. It's fairly intuitive, right? It would make sense that the stiffness of the material would be related to Young's modulus of elasticity, right? That's how much springiness our material has, right? So it turns out that the stuff that you learned in materials, right, actually has an effect in real world situations. I know, it's crazy. It's crazy. All right, but what about torsional springs, right? Well, hey, look, there's equations for that too. Again, I'm not going to, the point of this class is not to have you guys plug and chug coiled round wire spring things to figure out K, okay? Point is to make mathematical models for systems. Do you have any questions on stiffness? No? We're all doing okay? All right. So let's talk about friction elements. Let's talk about friction elements. Many systems have elements that dissipate energy due to friction, right? And we're going to model this through a damper or a dash model, okay? And you can see it here, and the most obvious example in my mind of this is if you've ever used a screen door, right, that has one, it has the door closer on, right, that makes it not slam, right? The cylindrical piece that's attached to the spring so that when you open the door all the way, you don't have to worry about closing it yourself. You can just let go and it'll come, and you hear the air hiss out of it, right? That's a damper. Another obvious example is the shocks in your car. Right? Those are dampers as well. I mean, we'll talk more about those later, right? Friction or damper elements provide energy dissipative forces when relative motion exists between two bodies, right? This definition makes it sound as if you always have to have relative motion between two bodies, and this is not the case. Dampers can exist in situations where we have free end and fixed end as well, like a spring, and we'll talk more about that later. But if both ends are free to move at their own pace, then you will use this equation: F is equal to B times x dot squared minus x dot 1. A general rule of thumb is that your damping force will always work opposite of your motion, right? Kind of like friction. This is what we consider to be a viscous friction, right? So for ideal dampers, ideal linear dampers, we use F is equal to B times x dot 2 minus x dot 1, quantity x dot 2 minus x dot 1, right? And those are velocities in meters per second. And if B is our viscous friction coefficient, sometimes you'll see that written as C, depending on what resource you are using. So just be aware that if you see C, if somebody defines C for you as a damping coefficient, that is something that happens sometimes. You see the units check out, right? So if I multiply B times, which is in newtons second per meter, and I multiply that by meters per second, I'm left with newtons, right? So the units check. And I know that if you guys didn't have me for ESG-360 and you had Professor Tomford, I know that her biggest thing is when you guys do not check the units. Drives are insane. Insane. Just check the units. Okay. Cool. So that's friction, right? So it's not all friction, right? This is viscous friction. Well, when does viscous friction apply, right? When does viscous friction apply? Well, in the real world, what if you had some kind of hydraulic fluid that you were moving through? What if you had a thin film of oil that was lubricating your system, right? These are times when we would have some sort of viscous friction, right? As opposed to dry or Coulomb friction or square law friction, right? Which we'll talk about in a second. All right, so for an ideal torsional damper, right, it's the same thing. Again, these analogies hold true, right? The only difference between a rotational system and a translational system from a modeling point of view, right? So from a modeling point of view, the difference between the two systems is the variables names, right? The torque is the force. Omega here is the velocity, right? It's angular velocity. These are equivalent to the translational one, right? It's the same equation, it just has different elements. So from a modeling point of view, these things are not different. Obviously, from a physical point of view, one is rotating and one is translating, right? One's moving, you know, and one's rotating. But overall, you know, they're the same. And again, you don't have to have an actual piston cylinder dash pot in your system to represent it with a damper, right, or friction element. We can have things like I just talked about, like a thin fluid film, or hydraulic fluid, or whatnot. Okay. You guys have any questions on friction elements so far? You're doing all right.
Yeah,
So-
can you repeat something for me? Can you repeat the distinction that you wanted us to make between the friction and stiffness elements?
Between you mean between rotational and translational elements, or friction and stiffness? The main distinction is right between friction and stiffness. The biggest thing is one is a function of position and one is a function of velocity, right? That's what we're going at, right? You don't need to have an actual spring or an actual damper in your system to model it as such, right? If you have some property that deforms, that stores energy due to deformation, that's the same as having a spring. And if you have something that dissipates energy using viscosity, essentially, then you can model it as a damper. Okay. Is that kind of where you're at? Solid. Cool. All right. So let's talk about ideal. Like, what do I mean when I say it's an ideal spring and it's not ideal damper, right? So what that means is that essentially if you have an ideal spring, it has no mass and it has no damper. It only does stiffness. That is it. Its whole ambition in life is to absorb deformation energy and release it at some point, right? That is what the ideal stiffness element or spring will do, right? An ideal damper has no mass and it has no stiffness. All it does is it dissipates energy as the day is long. Okay, that's all it does. Now, if you guys have screen doors at your homes, I think you should do this. I think it'd be a great exercise. Later, go and try to slam it as hard as you can. Okay, go try to slam it as hard as you can. Really put some velocity into that. And what you're going to see is that the faster that you try to push that door, the more force it's going to resist you with, right? Because that's what the damper equation tells us, right? Friction can also be nonlinear, okay? In the case of Coulomb friction, dry friction, right? We all know Coulomb friction. Coulomb friction is mu times n. That's what we consider it to be, right? And square law friction, such as aerodynamic drag, these are nonlinear. And so how are we going to deal with that? Well, for right now, we're not. We're just going to ignore things that are nonlinear for right now. Later in class, we're going to learn a way to linearize things that are nonlinear. It's called linearization. I know it's a really catchy and tricky name, but we will learn how to linearize things later in class. But for right now, we are just going to summarily ignore friction and drag, right? Why? Because up until this point in your engineering career, every problem that we've ever done in any class tells you that neglect wind resistance and friction. So we're just going to do that still. But we'll learn how to deal with it later. It's just, we're not going to worry about it right yet. Okay. Here are some pictures of friction elements, right? The first one is a rotary fluid damper, right? So it's got some fluid in there. B is essentially a dashpot, right? It's an adjustable linear pneumatic damper. These are more akin to what you have on your door as the door closer. And C is a heavy duty shock. The way that your door works right? Your screen door closer works is it uses air as the fluid, right, in there, and it displaces a bunch of air through a choke point. The way that you can control how much damping you get is by either opening or closing the screw in the base, right, which opens or closes an orifice in an orifice plate. Is there any questions on that so far? We're doing okay. Just cycling through all your pictures for now. Just to make sure everyone's awake. Okay. So let's talk about transformers, right? Because by the way, this is when you have to punch it. Then that's how you get the max. That's how you get the max boost. Okay? So mechanical transformers, right? So how do I want to start this? Millions of years ago, there was a war on the planet Cybertron. Okay? And the Autobots had to flee because they were losing to the Decepticons. No, all right, I'll stop there. What we're talking about is mechanical devices that transform motion or force, right? The most simple one that we can talk about is the lever, right? And it's an ideal lever, right? And we're going to talk about an ideal lever. What is an ideal lever supposed to do, right? It is supposed to either multiply or decrease my force, right? That's what it's designed to do. So it's taking some amount of force, and it will either apply a mechanical advantage to multiply said force, or if I shorten the arm, right, it will decrease, right? If I run it the opposite way, it decreases the amount of force, right? So if there's no inertia, what does this mean? Well, if there's no inertia, that means that there's no moment about my pivot point, right? And so I can write the equation for a lever of F1 times L. So the force right here, this guy, the left-hand side here, right? We've got some force pushing down times L1, right? That gives us what? That gives times the cosine of theta. That's going to give us how much force we have in the y direction, right? Because this is slightly angled. Is that the y? Nope, x direction, my mistake. And then F2, L2 cosine theta, right? So that has to be equal, right? We're just setting directions equal to one another. But then I'm going to do this thing, and we're going to do this thing a lot. And we're going to say, well, for small angles, and this is called the small angle approximation, okay? So for small angles, a couple things happen. First of all, why do we care about small angles? Well, for all the problems that we do in this class, we are going to assume that we start at equilibrium, okay? And we're starting at some equilibrium point, and then we are going to disturb that only a little bit from the equilibrium point, right? Why? Because it turns out, and we'll learn about this when we get to linear approximations, turns out that the closer you are to your starting point, the better your approximation is, all right? So for small theta, right? So what's the smallest theta? Let's say 0. Well, let's say theta is 0. What's cosine of 0?
1.
1, right? So look what happens for small angles. My equation becomes F1 times L1 is equal to F2 times L2. What if I had used sine instead, right? What if I use sine instead? Well, for small angles, for small deviations, the sine of a small angle is equal to theta, right? Sine of theta when theta is small is equal to theta. Smallest sine is 0, right? Sine of 0 is 0. Okay. So F1, L1 equals F2, L2. That's pretty cool, right? Oh, that's pretty cool. Well, why is that? Well, if F1 is my input and I want to know what F2 is, well, it turns out that F2 is just equal to F1 times L1 over L2, right? So if I increase L1 and I decrease L2, I have increased the amount of force that I'm outputting, right? So levers, ideal levers.
I have a quick question. Is the no inertia, is that like a simplification similar to the negating friction, or is that actually the case?
So it's this whole idea of an ideal lever, right? Whenever you see the word ideal, that means that it doesn't weigh anything, right? You guys have been doing this in like since physics 1, right? Assume that the pulley has no mass. I mean, in real life, the pulley has mass, right?
Right.
It's another simplifying thing, right? It just allows us to, instead of having to use a distributed model, we can use a lumped model, right? Which is where we want to live. Distributed models mean we have to do partial differential equations. Lumped models mean we can use ordinary differential equations. Good question. So let's talk about ideal gear trains, right? This is essentially the rotational equivalent of the lever, right? We can use gears to gear things up or gear things down, right? So if I have some gear train here, right, where the top is my input shaft, right, and I've got some T1, which by torquing it, I have now produced some omega 1, right? I've produced some angular velocity, right? And gear 1 has a radius R1 and N1 teeth. And that's going to connect to gear 2, right? And gear 2 has some radius R2 and N2 teeth. All right, well, I can define the gear ratio, right? We're all hopefully comfortable with the idea of the gear ratio. We can define it as either the ratio of the radius of R2 to R1 or the ratio of the number of teeth of gear 2 to gear 1. And we call that capital N, right? That's our gear ratio. And an ideal gear train assumes that, again, there's no mass, right? There's no inertia on these gears, right? On top of that, it assumes that all the teeth are equally spaced and that they all mesh perfectly, right? And that there's no wear, right? So ideal is like this perfect situation that doesn't really exist in real life, right? But it's going to help us to do a lot of these calculations. So then I have to define this idea of V mesh. Well, what is V mesh, right? So I want you to look, let's look at just gear 2, right? So I've drawn gear 2. I know. Another masterpiece. Thank you. Appreciate it. So I've got gear 2, right? And I'll draw gear 1 up here just for completeness. Now they're meshing here, right? They're going to mesh. We've separated them, but they're attached at that point, right? The red dot. Okay. Well, I know that this has omega 1 going this way. And so this is going to have omega 2 going that way. And so I will have some velocity that's tangent at this point that we're calling V mesh, right? V mesh. Yeah. And it's the same velocity because they're touching there. So it has to be the same velocity in the same direction. Otherwise, it doesn't make sense, right? Otherwise, the gears are breaking. Okay. Cool. So what's V mesh? How do we define V mesh? Well, V mesh is defined as we know, as we remember from rotation about a fixed axis in dynamics, right? If something's rotating about a fixed axis, we can figure out the tangential velocity at any point by multiplying the radius times the angular velocity. Right? So R omega 1. Well, because at that point they're meshing, R1 omega 1 has to equal R2 omega 2. So I can rewrite this as omega 1 over omega 2 is equal to R2 over R1, which is just my gear ratio, right? Okay. So now, if I equate the power in shaft 1, right, T1 omega 1, and I set that equal to the power in shaft 2, T2 omega 2, then I can say, well, the ratio of T1 to T2, right, my input torque to my output torque, is the same as the ratio of omega 2 to omega 1. Well, that's just 1 over n, right? Okay. So that means that if I want to find out T2, right? I'll write it over here. If I want to find out T2, what is it? Well, that's just my gear ratio times my input torque, right? And for this particular system that we have here, and I'll erase that so that we can actually read it. Right. So for this particular system, this is a speed reducer. Right. If it has a larger torque. Okay. So neat, right? We can use the gear ratio to figure out how we've multiplied our torque, right? There's other ones too, but these are the most common ones, right? There's other transformers. Sometimes you'll hear that there's transformers and transducers, right? Transformers typically are thought to keep things like a force to a force or a torque to a torque. A transducer, right, would transmit something across types, right? So it would be like, I have a certain amount of electromechanical energy that produces a force, something like that. But we'll talk about that later when we get to week 3. Week 3. All right, you guys have any questions on gear trains or levers or transformers? No? You good? You're all in the post-lunch coma? Yeah. All right. All right. Cool. So now we're going to talk about something that's really important, free body diagrams. I know that everybody, regardless of whether you took statics and dynamics or not, everybody's seen free body diagrams before. I'm going to talk a little bit about kinetic diagrams today as well, which are a little bit less common. And I cover them when I teach 360. I cover them, but I know that Professor Comfort doesn't really care about them that much. And to be honest, in practice, most people don't use them. I think they're helpful when we're getting out, we're getting started doing things, because what we're trying to do with a free body diagram and a kinetic diagram is create a graphical representation of the equations that we are about to construct. Right? So if you do the picture right, there's no reason why you should ever get your equations wrong, right? And just so you guys are aware of how I grade things, right? If you totally botched your free body diagram, but wrote the right equation based off of the free body diagram that you have, you'll still get full points for writing the right equation because you did it correctly based off of the diagram that you have. So just keep that in mind, right? Keep that in mind. I grade everything piecewise based on how you did on the last section. All right, so what are the rules for free body diagrams? We've got some steps. The first one is to isolate the body of interest, right? Okay, makes sense, right? So I want to take what I know, right? If I want a free body diagram, I have to take the thing that I'm interested in analyzing and remove it from the rest of the world, because I'm only interested in that thing. Another way of thinking about this, since I know you all love transport and thermo, is make sure that you apply a control volume around the thing you want to analyze, right? You are separating it from everything else. And because you're separating it from everything else, it is now free. It is a free body, hence the name, free body diagram, right? So then we're going to draw our axes, right? So what I've done here, right? I've got my body right here, right? I've isolated it. Then I drew my axes. I've got X and Y. You can see I've got a rotation in that direction, right? All right. Always use the right-hand rule to determine what is the positive sense of rotation. Some systems will only translate, some will only rotate, many will do both, right? Many will do both. You need to understand which direction you're considering positive so you don't make sign errors. Are sign errors that big of a deal? I don't take off huge amount of points for them, but they do stack, right? So you want to try to minimize them, right? But It's not that bad. So what's the right hand rule, right? I place my hand, my finger is pointing in the direction of positive X. Okay. Then I curl my fingers in the direction of positive Y. And now if you've done that, your thumb should be pointing back at you. So positive Z is back towards you. But more importantly, the direction that you curled should be counterclockwise, which is positive for rotations. Right? So that's the right hand rule. We want to use the right hand rule to define all rotation senses, right? We use right hand rule to define all rotation senses, right? So how do I pick X and Y? Well, there's multiple ways you can pick it. If you really wanted to, right? If you really wanted to, I don't know why you would, but if you really wanted to, you could pick this, right? Or you could pick this guy, right? You can pick whatever you want. It doesn't matter. These are horrible choices for this system, but go ahead and do it, right? Remember, when you do the block on the inclined plane, you can move your coordinate system wherever you want, right? Make it easier for you. The right-hand rule still applies, right? X into Y, still coming this way. X into Y, it's going into the screen, right? This is an arbitrary choice. Pick it however you want. I will grade your work based on the coordinate system that you put on the page, okay? But make sure you define it, right? Make sure you define it. It's an arbitrary choice. You'll come out with the same model in the end, right? You'll come out with the same model in the end. All right, I'm going to add in my applied forces. That's step 3. What are things that are applied forces? Well, in this case, it's weight. Tension is not an applied force here. And we're going to see why, because it is a support, right? So that rope was cut, right? That's an internal force to that rope. It's the tension. So that's a reaction, right? And then 5, we're going to draw our appropriate dimensions. So we'll put, you know, our radius and stuff on there. Oh, sorry. Okay. So that's the sum of the forces part, right? Everybody feel comfortable with free body diagrams, right? I hope so. If you don't, you know, make sure you come to office hours and make sure that you are getting some practice in them. I know I talked about it a little bit earlier, but I posted on YouTube part 1 of the dynamics refresher. I'll post the next part next week. You know, definitely take a watch. It goes through kinematics and kinetics.
I have a question, Doc.
Yeah, so
sometimes in problems with like bigger things to evaluate and like multiple forces going on in different places, I have a hard time like isolating a single body of interest. Like I get to the point where I want to just free body diagram the entire thing, and like I get it back and I get it wrong.
okay. So you're going to see, Blake, when we get to the stuff that we're doing in here, it's going to be pretty obvious what we're, I don't know if you opened up the homework yet or not, but the diagrams that I give you, we'll get more into it. But general rule of thumb for this class, at least, is any mass that you have, draw a free body diagram for each and every mass.
Okay.
That's generally a good idea for this. We'll talk about it more about it why as we go along.
Okay, sounds good.
So what about a kinetic diagram, right? What does a kinetic diagram do, right? So I told you that I want you to think about this as if it is a graphical representation of our equations of motion, right? And so the first step here is to isolate the body of interest, right? Same thing. And then we're going to draw mass times acceleration. Mass times acceleration is a vector term, and we call that our inertial vector, right? It's directional, so you have an x direction one and a y direction one. You wouldn't be wrong to call this y double dot and this x double dot. That'd be fine. This can also be j theta double dot, which is probably what we're going to end up calling it later, right? What is this, right? What is going on here? Well, here's the deal. Yeah, Jeremy, what's up?
The double dots are scalars?
No. That's the time derivative of position, right? So that's an acceleration.
Got it.
That's the second derivative of position. That's why there's two dots. All right, so you're going to draw in mass times acceleration of the particle. If you don't know which way it's supposed to be moving, just pick positive. Why? Well, because then if you pick it in the positive direction and it comes out negative, it means it was moving in the negative direction, right? No big deal. However, if you picked negative and it comes out negative, that means that it's moving in the positive direction. So it's become confusing, right? You've double negatived yourself, you see. The two wrongs do in fact make a right. It's not true. Maybe it is, I don't know. All right, some of the forces is mass times acceleration, right? So if you look at the left part, the left side of this, right? This is the sum of the forces, right? This is then equal to the mass times acceleration, right? If I'm looking at how this is rotating, because this system is both translating and rotating, right? I pull that rope and it causes the wheel to move, right? It's rotating, but that rotation also causes a translation, right? Great. So how do I describe that? Well, I have to describe that with both of these equations, right? With both of these. And so we have the sum of the forces is equal to the mass times the acceleration, and the sum of the moments is equal to I bar alpha or J theta double dot, okay? So both of these are important. Where do we get the moments from? There's no applied torques here, right? Well, there's that tension, and that tension is r distance away, right? And a moment is just the force times the perpendicular distance that it is away from wherever we're rotating about, right? From the rotational axis, right? So T times R is equal to I alpha for this, right? Sum of the forces in the x direction is equal to 0 because there are no forces in the x direction, right? And the sum of the forces in the y is going to be T minus W is equal to MAY, right? So we're gonna run through one. I'm gonna do this one, and then you guys will do the next one. Okay, that's what we're gonna do. So I want to draw a free body diagram and a kinetic diagram for the bar AB, right? So for AB, there's a known force P that's applied at the bottom of the bar, right? And I have all of my dimensions, and I'm gonna go ahead and I'm gonna make this look like this because I prefer when my center of gravity looks like that, but you do what you like, it's fine. Okay, so I'm gonna do this. Very good, fantastic, right? Okay, so G is the center of gravity of the bar. Where is it? Well, it's dead in the center, right? Because it's a bar and they're symmetrical. Okay, so if I wanted to draw the free body diagram for this, the first step, right, and it's going to go back into the bottom corner, so you guys still have the diagram is still on the screen, right? First step, isolate the body. All right, I will isolate the body. There it is, boom. Nailed it, right? There's the bar A, B, with points G and C. Okay, well, that's awesome. That's easy. Step 2, draw my axes. Well, all right, there's X and Y. Positive rotation in that direction, counterclockwise. It's a two-dimensional problem, so I don't really need to show the Z-axis, right? But I mean, this works out. Okay. When I add my applied forces, well, what are my applied forces here? What do you guys think? What are my applied forces?
P.
P.
P for sure. Is there anything else?
Wait.
Weight, there it is. Or mass times gravity, you know, if you're into that sort of thing. Not you can call it weight. Okay, cool. What about supports? What supports do I have here?
The pin at C.
It is a pin at C, yes. Awesome. All right, what is important about a pin? What does a pin tell us?
No translation in either the X or Y direction.
On it. Beautiful. Makes it so easy. Right? Yeah. And so because we have no translation in the X and the Y, we have to have reaction forces, right? Because something is holding it. Something is holding it in place there. We're allowed to rotate around it, but we can't move it in space. So something is holding it in place. There has to be a force there. So we have Cx and Cy, right? So our reactions. So those should be all of our forces. Then we can add in our dimensions, right? We've got these guys looking really good. And then we're going to do our kinetic diagram. There's our kinetic diagram. Notice I've picked this to be positive. But wait, Dr. D, if I push that down there, wouldn't that rotate the opposite way? And wouldn't you have to say that everything moves in the opposite directions? Well, sure. Yeah, you could argue that. But I could also argue that the math will take care of itself. And if I just choose positive, it'll tell me that it's negative later. So it doesn't really matter. I want you guys to think about this though too, right? This guy, if I push it, it's going to follow a curved path. That's an awful drawing. Let me try that one more time. It's going to follow kind of a curved path like that, right? Point G. So as we go, it'll follow this because it's pinned here, right? So this distance R should always be the same, since that is a rigid body. So it's basically moving in a circle with radius R off of point C. Okay. Those two things are what? Those two things are equal. They are equal, right? And so if I wanted to, right? Let me see. Yeah, okay. So if I wanted to, right, sum the forces in the X direction, what do I have? Well, we got Cx, that's positive, right? Minus P, right, that's negative, is equal to MAX, right? Or MX double dot. We'll leave it as AX for now. I could write some of the forces in the Y direction. So that's going to be Cy minus Mg plus MAY, right? And I'm going to sum my moments about the center of gravity, right? And if I do that, I've got, well, what's going to happen? I'm going to have negative P times L over 2.
Dr. D,
Yeah.
on the forces in the Y direction, should that be equals MAY?
Yeah, sorry.
Okay. I want to make sure.
Yeah. All right. So you end up with something like, how did I get the sense of the rotation? Well, imagine this is my bar and I'm holding it at point C, right? I'm trying to see how things move, right? I want to see the rotation about the center. So I'm holding it at the point. I press at the bottom. That would cause a rotation that is clockwise, which is negative, right? Same thing with Cx. It's R distance away from G. Okay. So by looking at the diagram, I was able to get my Newton's second law equations, right? And this is very similar to what we're going to be doing with the rest of this, okay? As we'll see. But first, I want you guys to take, I'll give you guys 10-ish minutes, work on this one on your own, all right? You have a drum of 4-inch radius that is attached to a disc of 8-inch radius. The combined drum and disc had a combined mass of 10 pounds. A cord is attached as shown, and a force of magnitude 5 pounds is applied. The coefficients of static and kinetic friction between the wheel and the ground are 0.25 and 0.20 respectively. Draw the free body diagram and the kinetic diagram for this. All right, so you guys take 10 minutes, work on it on your own, then we'll come back, all right?
Is point G a fixed pin?
Point G is, what do you mean, is it a pin?
Yeah, is it a pin?
So it's a shared axis for both of the disc and the, what's the, the shared axis of the disc and the drum.
Okay, cool.
All right, you guys want another couple minutes? Everybody feeling pretty good? What's up? Another couple minutes then, I guess.
Was that Jones?
Nope. All right, guys, that's time. Who would like to share what they did? I had a feeling that's what's gonna happen.
Wheel of Doom?
It's, I'm just gonna have to pick somebody. Let's see. It's so hard to pick. There's so many of you. Really difficult. Let's go with Sean Fuller. Would you please share your free body diagram?
Okay, I did on, no, I just hold it up. I have my free body diagram here. I didn't know where mu, k, or s were supposed to go, but I have my free body diagram here with gravity, mass gravity here, and then the p force going up.
Cool. Yeah, you're not wrong with where mu s and mu k are very situationally dependent, right? It's whether or not you have rolling friction or static friction. And basically it's, if you have static friction, then you're trying to overcome it. That's the maximum amount of friction you can have to start getting something to roll. And then once it starts rolling, you have kinetic friction. So those are interchangeable, but you had it drawn in the right spot, which is against the ground, between the wheel and the ground. The one thing I would say is that when I was looking at it, right, you didn't have the dimensions of the disc on there, and you only had the central drum, not the whole disc, right? So just be aware of that, right? So, but overall good stuff. Thank you, appreciate that.
A quick question about free body diagram. I put a reaction force at the base of the large drum because I thought it was like, if it was like resting on the ground. Is that incorrect?
You put normal force? Is that what you said? Chris, sorry, I had trouble.
Yeah.
Cut out. So, yeah, normal force is important. You have to have a normal force.
Okay.
If it's touching the ground, then the ground is touching back, right?
Okay, cool.
So we'll walk through it anyway, right? So you guys isolate the body, right? Here it is. Then we've got our axes, remembering that we're going to use right-hand rule. Like that. We are going to put our applied forces in. So we have P and W. Now, when you pull this here, right? When you pull this here, what is this going to do? That is going to cause a rotation in which direction, right? Well, this is going to cause this to go this way, right? That's going to cause an angular velocity like that, right? Is everybody comfortable with me making that claim to see what I'm talking about there, right? We replace our, so a free body diagram, you don't have to put a velocity, right? This is all about forces. You do not have to add a velocity. We're going to replace supports with forces, right? And that's where our normal force and our friction come in, right? That's where our normal force and our friction come in. Right? We have our dimensions, right? We've got 8 inches and 4 inches. And then our kinetic diagram, which just looks like this, right? That's what we do. If you're only going to do one of these, do the free body diagram. The kinetic diagram is nice and will help you early on, right? But the free body diagram is much more widely used and much more helpful, in my opinion. You guys have any questions on free body or kinetic diagrams?
You want us to put the M, like the MAY, or do you want us to do like MY double dot, MX double dot?
It's gonna be, full disclosure, I took these out of the statics and dynamics textbook. That's where these come from. And they don't use the double dot construct. We want to use that. And there's a specific reason why, right? When we get to Laplace transforms and you're going to take the Laplace transform of a second order system, you want it to be in the x dot, x double dot, or whatever variable you decide to use. It's going to be a lot nicer. And you'll see why when we get there, but that's not going to be till like week 5 or 6, right? So I will pretty much exclusively for the rest of class from now on be using the dot and double dot.
So for the free body diagram on the left, the W is that, or the omega, that's the rotation. Do we need to include that?
No, you don't. I just did that as a way of illustrating that, physically, what would you expect to happen if you applied a force at that point, right?
Okay.
If I pull a cord here, right, that's going to cause a rotation that's counterclockwise, right?
Which would indicate a positive rotation.
Mm-hmm. Yes. Okay. Any other questions? This is not the last we will see of free body diagrams, but I just wanted to make sure that they're very important. And I know that I harped on them when we were for those of you who took statics and dynamics with me, I know that Professor Tomford also holds them equally as prized. I know that, Professor Bullock is really stickler for free body diagrams as well, right? And there's a reason, because if you do it well, and you do it correctly, it helps you significantly, right? Helps you significantly.
Quick question.
Yeah.
For the friction of mu S and mu K, those are situational only?
That's static and kinetic friction, right? So it depends on what's happening, right? If you remember back to statics and dynamics, right? We talk about static friction as being the maximum amount of friction that you would need to overcome to actually start motion, right? So that's mu sub S times N. If you don't overcome that friction, you will not start to move. Once you get higher than that friction, there's a dip, right? And then you have to start using kinetic friction because you already started rolling. So the situation is, are you stopped and you need to start moving, or are you already moving? It doesn't really matter for this class because, as we mentioned earlier, using dry friction, like Coulomb friction, which is mu sub K and mu sub S times N, is not something we're going to do because it's nonlinear and we're going to ignore it.
All right, copy that.
We will do a couple of problems where we take it into account and we have MATLAB crunch the numbers for us. And you know, we'll see if it's worth including it. Right? All right. So just as a recap of what we did last time, right? Dr. D's super terrific #1 5-step method for developing models, right? Draw a picture. That's the whole point of the last activity we just did, right? Was get your free body diagrams and your kinetic diagrams in order, right? For electrical systems, that's circuit diagrams. Essentially, we just want annotated pictures to define all of our variables and parameters. You want to identify your inputs and your outputs. You want to identify mathematical truths. That is to say, we want to identify the equations that govern our system. And then we want to do algebra to move all those things around and get one single equation that is in terms of just my inputs and my outputs. And then I want to evaluate my solution, right? Does it make physical sense or not, right? And again, I told you guys this on Tuesday. I'll say it again. Please consider this to be the rubric by which I will grade any problem that you turn in. Okay. This is what I am looking for. I'm looking to see, did you do these steps, right? I've mentioned it earlier in class. I'll say it again. The way that I grade, if you did step 1 wrong, but you identified your inputs and outputs and managed to get the correct equation based off of the wrong free body diagram, then you still got your equations correct, right? So you don't automatically lose all the points if by some reason you do not get the free body diagram correct, right? So I don't want you guys to think, oh crap, well I got the FBD wrong, so that's a straight 0. It's not. That's not how it works, right? It's very much about, did you implement the process correctly? That's what it's about. Okay. Any questions on this? On the super terrific #1 5-step method for developing a model?
What if you somehow screwed up the entire process but got the right answer?
Then I would tell you on your homework to stop using Chegg, and you'd still get a 0.
Copy that.
It's happened. I've written it on people's homeworks. Anyways. Okay. So, right, how do we implement this, right? Well, let's put this in the context of an example problem, right? And I think that will help to elucidate what we're supposed to be doing, right? So I've got a high-speed solenoid actuator valve system here in figure 3, and I want to derive the mathematical model, right? The equations of motion for this system. So for those of you who are unaware of how a solenoid works, we'll watch a video on how to make your own solenoid at home later in the semester. But essentially, you apply an electrical impulse, right? Apply some voltage, it creates a magnetic field, and that magnetic field moves a piece of metal through a coil, and right, you can use it as a valve. A major application of this is door locks at hotels, right? Because once the voltage is removed, then the spring returns it back to the seated position, right? And so you can see here, there's this nice schematic that we have, right? This is the seated position, right? Once we turn on our current, this will get pushed away, right? We'll close our spring, and then once it turns off, the return spring brings it back to the seated position, right? Displacement is considered positive to the right, measured from the seated position. The electromagnetic force pulls the armature toward the center of the coil, and closes this air gap. The air gap's right here. The return spring is undeflected when the armature valve is seated. Okay. So when this is seated, the spring is just chilling, right? It's the exact right length so that there's no spring force when this is at 0. Okay, it's undeflected. Okay. So quick show of hands. Are you intimidated by the schematic that I just showed? Do you think that you could do the problem based off of that? We'll go back and look at it again. This is a pretty crappy schematic, right? It's not great. And if I asked you to draw a free body diagram off of that, it'd be It's not impossible, but it wouldn't be fun, right? So let's simplify that schematic, right? Let's simplify. Let's see what we can do with that. Well, remember last class we talked about we want to be dealing with lumped, linear, time invariant systems, right? So we're going to lump the armature and the valve mass, right? So I'm going to take this guy here, this spool valve, and this armature, right? So this entire thing, and I'm going to lump it into one mass, and I'm going to call it A. Okay. Okay, so that's one mass. I'm going to take the return spring, and I'm going to say, you know what, that return spring, well, that's an ideal spring. And an ideal spring is going to have K. And I'm going to have that hydraulic fluid, but that hydraulic fluid is just essentially dissipating energy for me in a viscous friction manner. So I'll treat that like an ideal damper. And that will have B. Okay, and if I do those things, I can redraw to take into account these assumptions, right? And when I do that, it looks like this. This is the simplified model of a high-speed solenoid actuator. Now this is something that we can do, right? Maybe, I don't know. I don't know, Dr. D. I don't believe you that it would do that. It's there on the page, all right? I wouldn't just put things up there, guys, all right? That's not how it works. So now that we have our simplified model and it looks like this, let's apply the 5-step method to it and see what happens. I'll give you guys a second to draw the schematic if you want it. The first step is what? Right, the first step is free body diagram. Right, so we're going to draw a free body diagram for this mass. Right. Now, I'm going to draw a free body diagram. That's my mass. I know. It looks just like a solenoid. It's uncanny. Here's my electromagnetic force. Here's my spring force. Here is my damper. Okay. I need coordinate system, right? And I'm going to say that this constitutes a coordinate system. And you're going to say, well, that doesn't have a y direction and it also doesn't show rotation. And that is true. It doesn't. But let me ask you this question. Does this system rotate at all?
No.
No, it does not. Should it move up and down at all?
No.
Also no. Correct. So I'm just not going to include it. Is it wrong for you to draw this guy if you want? No, go ahead. But in this case, these two things are equivalent. Okay? So just be aware. Those two things are equivalent. You have assigned, all right, so I'm looking at this, right? And you're like okay. Taylor, I didn't ignore it. All right? I didn't ignore the rule. There's a coordinate system there. Okay? There's also no dimensions on this. So we weren't given any. So there's that. On top of that, I think it's important to realize this spring and this damper are in different locations, right? But they are essentially acting through the center of gravity. We are just not drawing them as such because if I drew them on top of each other, everybody would be really confused. Okay, so I've just separated them for visual aspects. All right. Okay. So what is this saying, right? This is saying that my electromagnetic force is going to be pushing to the right. right? Because of that, I want to go back to our original schematic for a second, right? If I'm pushing this to the right, are we compressing this spring or are we extending this spring?
Compress.
It's compressing, right? And if I compress the spring, right? Notice I have my spring again over here. If I was to push this spring, whoop, I dropped my spring, guys, it's going forever. Just kidding, I found it. So if I take my spring and I compress it, right? It's pushing back against my fingers, right? So if I compress this, the force is going to be pushed in the opposite direction of the motion, right? If I have my damper is also going to fight that motion, right? Because that's what dampers are designed to do, right? Okay, so that's why my forces are drawn the way that it is. Is everybody all right with the free body diagram as it is drawn? Everybody okay with that? Yeah, okay.
Dr. D, could you compare the free body diagram to the full schematic?
Right here?
Yeah. Just see.
That whole thing is now M.
Okay.
This spring is FK. Do it in the colors. There's some hydraulic fluid in here, right? This is providing some energy dissipation, right? Because in order for me to move this, I have to push that fluid out of the way. It goes in and out of this channel and this drain here, right?
Awesome.
This electrical input creates some electromagnetic force. That's going to push this to the right.
Sweet. Thank you.
Mm-hmm. So instead, we just drew it as a square because you know, Microsoft lets you draw squares, I guess.
Better to simplify it.
Okay, so here it is, right? So what's the next thing we're gonna do? We're gonna pick our inputs and our outputs. All right, so what do you guys think the inputs are?
The electromagnetic force.
Yes, excellent. The electromagnetic force, right? What was driving the system, right? The input is what drives the system, right? What is causing the motion? So the output is what? Is what is coming out of the system. What is the result of me applying this electromagnetic force? I applied the FEM, right? So what happened? Taylor, kinda, but not really. You're jumping a little bit, jumping a little bit. Just there's one thing that's an output. There's one thing.
The movement.
It translates.
Translates, yes. The output is X. I apply the electromagnetic force. The solenoid moves, right? The metal piece moves. When I release that force, it comes back because of the spring force. All right, awesome. So here's where we're going to apply our mathematical truths, right? So what is governing this system? Well, we have their sum of the forces is equal to mx double dot. Okay, Newton's second law. Sum of my forces mx double dot. But we also have f sub k. And we know that that is equal to kx. And we have f sub b, which is b x. Okay. And so now what do we do, right? And for a mechanical system that translates, these are the laws that govern that system, right? Well, what if you didn't have a damper? Well, then you don't include the damper equation, right? What if you don't have a spring? Well, if you didn't have a spring, you probably wouldn't have a damper. There's really no reason There's really no reason to have a damper without a spring. Okay. That's it. That's mathematical truths. Sounds more complicated than it is, but that's where we are. Okay. So far, so good. Everybody okay? Any questions? Everybody's following the trail of breadcrumbs, right?
For now.
For now. Awesome. So now we're going to reduce our equations. Okay. So for this, I want you, and you know what? I didn't draw my kinetic diagram, right? Let me do it anyway. Just real quick. I'll do a real small one. There it is. That is the kinetic diagram, right? Because you could put this there, and you could put that there too, right? But really all it is. Okay. So Newton's second law tells me that the sum of my forces is equal to mass times x double dot, right? So if I sum my forces based off of this free body diagram, right? If I sum my forces based off of this free body diagram, wait for it. The sum of the forces is equal to FEM minus FK minus FB, and that whole thing is equal to mx double dot, right? In the y direction, everything is equal to 0. There's no force in the y direction. There's no acceleration in the y direction. That's right, Taylor. That is. But you look at that. It's like it was meant to be, right? Because what do we do now? Well, now I have an equation for f sub k and I have an equation for f sub b, right? So let me plug those in, right? I've got FEM minus kx minus bx dot is equal to mx double dot. But the last step is that I want all of my inputs on one side and all my outputs on the other, right? So I can rewrite this equation as mx double dot plus bx dot plus kx is equal FEM, right? And this is my equation of motion. That's it. That is the equation of motion. Now notice something. We didn't have any numbers, right? And that's powerful because no matter what the system mass is, no matter what damping it uses, and no matter what spring that we put in there, we should always be able to figure out what the dynamics of this system are. These are only constants, right? Those are only constants in here. But that's it. That's the whole thing, right? So the next step is what? Analyze your results. Do they make physical sense? Well, we're not going to do that right now. We're going to do that week 5 and beyond. Okay. Right now, we just want to make models. In week 3, we'll talk a little bit about what is this FEM, right? Because this is an electromechanical system, isn't it? There's some electrical component that controls it. So we'll talk more about that when we get to electrical and electromechanical systems. You guys have any questions on this? Everybody doing okay?
How would you rank, like, would you say that this is like a very basic problem or like kind of average?
This is a basic one. This is pretty basic. You have, I mean, it's pretty much for mechanical systems. This is as easy as they come. Any other questions? All right. Well, if nobody's got any questions, then yeah, we're not gonna do that. Then we're gonna do time trials instead, because I deserve a break, and you guys can do some of it. Okay, been talking for like 5 hours. Okay, so for those of you who don't know, the rules for time trials are simple. And we're not going to have 45 minutes because that would take us over the time limit for class. Last class, I gave them 20 minutes. So you guys are also going to get 20 minutes. That should give us plenty of time to discuss it after the fact and do the poll everywhere and still get out of here at 3. Okay. So each of you will have 20 minutes, each team, 20 minutes. I'll put you in breakout rooms. No Chegg, no computer is unrealistic. Otherwise, this would be a really short Zoom call. No text, no textbook, right? Notes and calculators are fine. If your team is the first to finish, you get the maximum points. Call me into the breakout room. I'll check your work when you feel like you're at a point, right? I will also stalk breakout rooms, jumping back and forth and back and forth. So last time, it was more of a people just kept calling me around, and I just jumped around that way. But we'll see. All right, so here's the problem. Write it down, take a screenshot, something so that your group can take a look at it. Right? So I've got a mechanical system shown in figure 5. It is composed of a single mass, a spring, and a damper. The vertical position of the mass is X, which is measured from the undeflected position of the spring. Derive the mathematical model for the system. I'll give you guys a couple of minutes to screenshot it or do whatever it is that you want to do, and then I will kick you into the breakout rooms. I think I have everybody sorted already. All right, here we go. If you notice that you're not in the right group, let me know and I'll switch it out. All right, here we go. I'm gonna hit the open. I'll see you guys in 20 minutes. There you go. All right. Seems there's a couple people. All right, guys, I'll get you in with your groups. Sure. Mikey, what group are you in?
16.
There you go. Yeah. That would make sense. All right. See ya.
Thanks.
All right, everybody. As I was just telling the one group that I was in with, this is the Admiral Akbar of problems, right? It's a trap. That's what it is, okay? This one was a trick. What are we gonna do here, right? Let's start. We'll draw a free body diagram, right? So the free body diagram for this, mass, damping, spring, and the weight, right? I will draw my coordinate axes as such, x, y, which means that I've got positive rotation in this direction, okay? Cool. This is going to be equal to my kinetic diagram, which I will just draw as mx double dot, right? Now remember, this is important, right? This x double dot, this is not gravity, okay? Gravity is the weight. This doesn't need to be, this is not in free fall, right? This is attached by a spring and a damper. So it could be going at gravity, it could be accelerating at gravity, or it could not be, right? But the one thing that is really important to remember is that this is happening at equilibrium, okay? So let me do this. So identify our inputs and our outputs. Well, this one's a little bit tricky, right? My inputs are either, right, you can say it's the weight, which is fine, or you can say it's x. It's either one. And you're going to see why in a second, why it doesn't really matter. But our output is definitely position. Okay? So again, I'm saying this starts at equilibrium, right? So that's going to have a specific connotation and specific thing associated with it, right? But we'll write our equations, right? FB is equal to BX dot FK equal to KX. And in this case, our weight is equal to mg. Just so I don't forget it, right? Just to remember it. So far, every group is great up until this point, right? And you're even great when you did this up to this point, right? So if I do my sum of my forces, that's going to be equal to mx double dot, and that's negative bx dot minus kx plus my weight, right? Everybody was right here. Everybody was right here. And then everybody ran into the trap, which was you started from equilibrium. And if you start at equilibrium, the spring is already holding a mass, right? So let's investigate what happens at equilibrium. What does it mean at equilibrium? Well, equilibrium means that x double dot is equal to 0, right? That's statics. Sum of the forces is equal to 0 from statics. If the acceleration is 0, then x dot should also be 0. So if I evaluate this equation at static equilibrium, right? Static equilibrium. Then what happens? Well, x double dot is 0, so 0 is equal, x dot is 0, 0 minus kx plus mg. Okay. So I'll rearrange this, and instead of using x, I'm going to call this delta, lowercase delta. So I'll have k delta is equal to mg. Why would I do that? Well, I'm going to call this the static deflection of the spring, delta. Okay. And so I can solve for the static deflection of the spring, which is just mg divided by k. So I've got mg divided by k. That's delta. All right, well, another way of thinking about this is this force, k delta is equal to mg, right? That force is what? Right? That force is just the preload in the spring. The spring already has some force that's pulling it back up, right? It's holding the mass off the ground. It's holding it aloft. So let's look at this, right? If I then write my equation, and I'm going to say, well, I'm going to move this a little bit off of my equilibrium position. I'll have mx double dot plus b z dot, right? I'm going to rearrange this a little, plus k times delta plus x. So I have my static deflection plus the distance that I moved, and that's going to be equal to mg, right? But hey, k delta is mg, this is just K delta, right? These are gonna cancel. Those end up canceling. So I will do this on the next page, right? So if those cancel,
Where did the Z come from on that previous page, if you don't mind my asking?
what's up? Did I
You
write
wrote
Z?
a Z in there. Where'd that come from?
Sorry, that should be an X. My bad. Well, you didn't see the Z? The Z's are slipping in, man. So if I do this, we end up with that as our equation. So this is pretty awesome as a result. Why is this pretty awesome as a result? Because it turns out that if you analyze systems starting at equilibrium, you don't have to worry about the weight. You just don't, because it's already taken care of in the preload. Everybody was like right there. One group pulled it off. Everyone else gets second place points for the week. Okay, we're gonna stop there because we have 2 minutes left in class. Do you guys have any questions?
I have one real quick. So the K delta and the mg, I didn't quite see why that canceled out.
All right. Okay. All right. K delta is equal to mg, right? So if we do this out, right, you'll end up with K delta from this plus Kx, right? And so that's just mg plus Kx is equal to mg, right? And so
cool.
I know this is not the best, but I ran out of it. It's a trick. It was a trick. It's not even Halloween. That's not even Halloween. Okay. We'll do this stuff. We'll do these next class. Oh, no. No, thank you. No, no. Okay, we don't have time for this either. It's too bad. That's a good one. I would like to go to the next slide, please. There we go. Okay. Awesome. So can you guys see the poll everywhere link on the top of the page? No?
No.
No.
How about now? Can you see it now?
Still no.
Oh, no. Let's try this one more time. If not, then class is just going to be over.
I just saved it from last time, and you can like save it as a bookmark, so it'll always bring you back to it if you guys want.
But can you see the actual graphic on the screen or no?
We can see the smiley faces, but not the link.
All
yeah,
right.
it's just slash the Quizzard.
At the very top. All right. So using you know the hospital pain index, right? You guys a couple seconds to do this one, and then I'll throw up the last one, and then you can just go. And then I have another class. So apologize, I can't stick around too long. Come on, next one. Of course, it doesn't want to do the next. No, not a breakout room. All right, so stop screen share. All right, I'm gonna have to do it manually. And last thing, then you guys go. Be free. Have a great weekend. Do whatever it is you do on the weekends. Have a great time. Relax.
I have a question before you go.
Yeah.
So you posted an announcement saying you want us to do a LinkedIn thing with you in order to get our points. I'm not sure if you have some kind of privacy setting, but it doesn't give me the option to connect with you.
I do not have a privacy setting.
Okay.
There is a space in my last name. So.
All right.
I
I mean, I found you. It just won't let me click the button.
What if we're already connected with you?
If you're already connected with me, send a message just saying participation points, please. Yeah, you know what, Taylor, I'll go on LoudCloud tonight or tomorrow and I'll post a link to mine. If it's still not working, just let me know. And we'll do it on a per person basis.
Okay. I mean, I found you. I just can't click it.
It's weird. I've heard that before, actually. That's strange. Yeah. Well, try it in a different browser, I guess. Foster, if you don't have LinkedIn, I think it's a really good idea for you to get LinkedIn. LinkedIn is a great place for you to connect with other people. It is a great place for you to look for jobs. LinkedIn has a ton of jobs posted for all disciplines of engineering. So I would really recommend that you do it. And I really think it's a very good idea for everybody to be on LinkedIn.
Are we supposed to be responding to your understanding is inevitable?
Yeah, or you can leave. One or the other.
Hey, Dr. D. Have a good one.
Bye, guys. See you.
Have a good one.
Don't forget to get lab partners if you don't already have them.
Doctor. Dr. D.
What's up?
How far in the homework should we already be at?
I don't know, Jeremy. Probably not that far. We didn't really do very much. So you can probably do some of the short answers and maybe start a couple of the problems. Just take a look through it and see.
Yeah, because I'm thinking I'm probably going to be doing like 50 free body diagrams.
Yeah, you're going to be doing a lot of those. That's a fact. That is a fact.
Hey, Professor, did I miss the poll? It's because my stepmom was calling me for some translation.
That's all right. Olivia, if you want, it's up here. You can do this one. You don't have to do them to get participation points. It's just for me to kind of check to see what the pulse of the class is. So it's not like I'm not checking who's doing it or anything like that. So.
Okay, well, mine is not like the 5th happy face, but the 4th one.
Okay, appreciate that. Thank you.
Thank you.
All right, have a good one.
You too.
All right, I'm getting call it here because tomorrow we'll be busy with all kinds of stuff from classes, and then the weekend I am at work.